and try to
Yes. Thank
answer.
you. Thank you, Aldo. Thank you for this very nice presentation, well illustrated and quite rich. I mean, I'm sure that there will be many questions. Those who wants to ask questions, they can send their questions in the messages within this this broadcasting now. It's so please send questions into the messages of the Zoom system here. Maybe Murad would like to say something.
Yes, I have two questions. Aldo, what do you think about the submarine cable? And the second question, and the use of submarine cable for the earthquake early warning system. And the second question, what do you think about the seismicity of the Atlantic margin, Portuguese Atlantic margin, and the earthquake early warning system?
Okay, thank you, Murad. I think you are referring to the DAS system, so fiber optic cables or seismic sensor cables. I think you are referring to the use of fiber optic cable for detecting seismicity.
Yes.
Is that okay? So nowadays, this is the new trend, and there are many studies showing that we can detect and record earthquakes on cables, and they can effectively be used, although there is no practical application about that. There are a few studies that are ongoing. In particular, how to interpret the amplitudes on this sensor, on this seismogram that we get from the fiber optic cable. But the possibility to have thousands of sensors along a cable to detect an event, why not? It is something to be explored that I think is one of the next future technology that could be used for early warning. We have to solve, in this case, the issue related to the interpretation of the amplitudes that are recorded by those systems. As for the protection of the Iberian Portugal region from earthquakes occurring in the Atlantic region, I think the best suited early warning system could be similar to what has been developed in Mexico, with an array of stations located parallel to the coast or along the coast, a kind of barrier system, so that as soon as waves that exceed a given threshold achieve the network along the coast or submarine, if you want, if you have the possibility to install it, then you can provide the alert to the on land and onshore cities. That could be a system. So even in this case, the system, the monitoring system must be adapted to the specific situation where earthquakes occur outside of the region, then has to be protected, in particular in this case along the sea.
Thank you, Aldo.
Yes, Aldo, a question, since most of the audience are located in Algeria. Would you say that another region where the earthquake early warning would be applied can be in northern Algeria? This is one first. Yeah, this is one first question. I have a second question. I think you addressed it, but indirectly. is how about the size of the earthquake initially when you received the first P wave and in between the P wave and the S wave?
Okay, so Algeria and I would say all the Northern Africa region is. I was searching for my initial figure. This one. Yeah. So all this region you see is affected by high seismic risk, and they can be potential target for application of early warning systems, especially in the Alboran Sea. You may have events with relatively moderate or high magnitude, higher than 5.5, 6, that can produce a strong impact on the Algerian coast and the cities. So it is very, very important to densify the monitoring systems and to open joint ventures with Spain and Portugal and Morocco. So build a kind of inter-Mediterranean action to that. And nowadays we are working with PhD students from Università Complutense de Madrid. They have implemented our new systems, and we are trying to see what is the performance of the system for earthquake occurring in the Alboran Sea. And the results are very encouraging, even if on the African sides, we have only few stations relative to the northern side. So this is, to me, the typical condition where this kind of a system can be implemented, tested, and seen. Then, once the system provides alert, we have all the problem or to make this alert effective in training the population, to linking with automatic data transmission, etc. All these problems that are related to the effective use of the early warning. But yes, so the second question was about the magnitude. In some cases, we get magnitude underestimation at the beginning, but in some cases, we get from the beginning the good magnitude estimation. I would say that in general, it depends on the magnitude of the events. If the magnitude of the event is around 5.5, I would expect a source time function of 1 to 2 seconds. So we get very rapidly to the right magnitude estimation. If the magnitude becomes larger than 6, 6.5, 7, where the source duration is of the order of 10, 20 seconds, we get slower to this value because depends on how the sleep at the source rise to the peak in the moment. So it is more or less. But what I want to point out that you don't need an exact evaluation of the magnitude for rising in alert. As soon as your predicted peak ground motion exceed a threshold that you believe is relevant for your application, you give an alert, independent or not depending on the magnitude that you have estimated. That was the case of Turkey, where even though at the beginning our magnitude estimation was not correct, the predicted PGV was much higher than the threshold set by a virtual user. And so you can give the alert anyway. I don't know if I'm
It's
clear about that.
No, it's clear. It's clear. It's quite clear. I have a question here from our colleagues from Yahya Mohamdi. He's from the Research Center of the Geophysics in Algiers. And he's asking, is the impact-based system use the local geology as an input?
Sorry? There is a...
Well, there's a question here from a colleague from Yahya Mohamdi from the Research Center of Geophysics in Algiers. And he's asking, is the impact-based system use the local geology as an input?
Yes. I see two sides of the methodology where the geology can enter. One is to better characterize the site amplification in the ground motion prediction equations. So a good geological characterization of the sites where the instrument is relevant. In particular, the sites where I want to give the prediction, because we know that the amplification at the sites plays an important role in the peak ground motion. The other side where I see the characterization of the site is important is into the relation that we use to correlate the P wave amplitude with the PGV or S wave amplitude. In general, the studies that we have done do not show important site amplification, but maybe that site could differentiate the behavior of waves depending on P wave and S wave. So these are the two parts of the method where the information about the geology essentially enter in this. Yes, certainly.
Okay, yes, very good question.
Mustafa.
Just a minute. So you have indeed. I mean I know that you have the experience with the Irpinia earthquake and Irpinia and early warning system that you didn't mention. But there is another question here from Mustafa Abuda. Also, I think he's also at the Research Center of Geophysics. So I open the line to Mustafa Abuda. So please, you can ask your question. On n'entend pas. On n'entend pas.
Bonjour. Bonjour.
Posez votre question. Posez votre question.
Can you hear me?
Posez votre question.
Yes.
Thank you, Professor, for your talk. It was very, very important and fruitful. I'm director of CRAG. As you know, the CRAG is experienced with managing, monitoring seismic alerts of northern of Algeria, and now we have a digital seismic network with about 100 seismic stations. Okay, because there are other colleagues that will make questions. I will be brief. Monitoring earthquake, it's a daily job of the CRAG, researchers of CRAG and engineers. I have two important questions. Which is the kind of instruments used? Because we have seismometer, broadband, short period, ground motion. Which is the best instrument which will be used to make an earthquake early warning system? This is my first question. My second question, also this earthquake early warning system, it depends of a telecommunication network. Okay, we have 4G, 5G, maybe special lines, and sometimes it not depends of the institution. Okay, it depends of the state or the network of telecommunication of the country. Okay, and this also can make some problems when we transmit the data. Okay, and a third is not question, but it's an invitation Dear Aldo Zollo, I invite you solemnly to, if you want to come Prague, and we can make a collaboration in this way, okay, to make a more perform our seismological network. Thank you very much. Merci, Mustafa.
No, de rien.
Okay. First of all, thank you for the questions and also for the invitation. I will be very glad to start a collaboration with your group. I know Craig since a very long time, and also I have a lot of interaction with research, so I know that is a very prestigious institution in Algeria. So I'm very, very happy for that. So about the instruments, so our idea in development of the seismic network that monitor the Irpinia fault system was to combine strong motion and seismometers. This was for two reasons essentially. We don't want that the shaking saturates the amplitude of our geophones. That is typically the problem of seismometers at broadband. During the L'Aquila event, magnitude 6.5, stations up to a distance of 60 kilometers from the epicenter were clipped the signals from broadband. So while accelerometer have a dynamic range which is able to sustain any amplitude, and now modern digital accelerometers are so effective also for recording macroseismicity, because of course, as you well known, during the peacetime, you would like to monitor seismicity even at low level, and so use those data to understand tectonics and to understand all the seismological models and so on. So to me, the best adapted sensor for earthquake early warning is the strong motion sensor, so accelerometer. And also because you, in the phase of experimentation, you want to check whether your records or your prediction really match the observed ground motion. And so the observed ground motion is likely to produce strong shaking. And so the strong shaking is well recorded by accelerometer. The second point that you raise is very, very important. Indeed, I can say is the most important problem. So makes that telecommunication, you say, okay. So that data transmission system make that signals have a delay, which is not a latency, that is not controlled by the data communication, the transmission systems. In our pilot network, we developed a proprietary data transmission system from each site to local control server, and then using the digital terrestrial bridge to transmit the data. Some connection are done using commercial providers, but it is very important that you control the real-time deadline of your data. That is not the case, I say, for instance, in Italy, for the Italian network, they do automatically operations of data. But when I say control the deadline, they cannot control whether the data transmission occurs at a given time window that typically should be less than a second in this case. So this is an important issue, of course, and that has to be analyzed at the same level of accuracy than for the instrumentation. Okay.
Okay, Aldo, thank you. Some now more and more difficult questions are coming. So be prepared. There is Mustafa Abuda. Mustafa Abuda, can you ask your question directly? Mustafa Abuda?
His
Okay, I can
microphone is the microphone is off.
off. Yes. Okay, I can try because he wrote me the question. He says, if we have a noisy station near traffic or other noise sources, there will be saturation at the station, making it difficult to detect P waves. Are there any methods that can process the seismic signal quickly, or can machine learning help in the detection of P waves?
Yes. The answer is yes, and it is one of the topic for the new developments. Actually, we use a, a standard, we call it in seismology STA over LTA, short-term average, the ratio between short-term average, long-term average. And to detect signals, we apply some pre-processing. For instance, we don't look the signals in the velocity, but velocity and displacement, and we combine, okay, complex algorithms to detect the P wave. But I agree with the question that, and it is the direction we are taking also, is to use artificial intelligence learning, machine learning method or deep learning method to improve the detection of the P wave. That is something that is really ongoing. So it is a good proposal.
Okay. Another question that I didn't understand, frankly speaking, but Fawzi Belalem, who is at the origin of this site of the geohazard community, he says that what are the limitations of the earthquake early warning accuracy?
Yes. So the limitation comes from the uncertainty that are implicit in the empirical regression law that we use. During my presentation, I show one example. So relating, in which we relate the P wave amplitude in displacement with the final PGV. And indeed, we see that the data are quite well correlated, but there is a standard error on this. So for the moment, we take into account, we use a totally data-driven and empirical approach, and we include the uncertainty in the prediction by taking into account the uncertainty in the empirical relationship. I don't have quite clear numbers, but for instance, on magnitude, we have generally uncertainties of the order of 0.5 unit in magnitude. And in the prediction of the PGV, we are in the classical uncertainty of standard ground motion prediction equation, so less than 1 sigma. So if I can broadly quantify, but uncertainty in this method is taken into account in a quantitative way. That is, at the end, we do not provide the exact value, but we provide the probability of occurrence of exceedance of this value. And so the user eventually can adopt a system that use the probability that is based on the uncertainty. So uncertainty is somewhat included in the system. I had no time to go into all the details of the technique, but this is done generally.
Okay. I have another question from Shafiq Aidi. He's also at the Research Center of Geophysics. He's a seismologist. He was in Strasbourg, actually, so he has a good background in seismology. So he says that in Italy, have you got a fake alert? If yes, how did you manage fake alert within the EEWS?
Okay. So first of all, I should clarify that in Italy, there is no an operational earthquake early warning system running. So all these studies are done at the level of the research. And the network, the manager in Irpinia didn't record since the beginning of the operation in 2009 to now events with magnitude larger than 4. So for every event that occur, we do a performance of the system. And as I tried to explain with the example of the Turkey, we cannot avoid to have a percentage of missed and false alert. I think that Shafiq is mentioning fake. Fake means missed or false. Okay, you may have these two. Okay, and so the choice is always a compromise, and this compromise is given by the threshold that you decide to use for the alert. We showed that in Turkey that if you decrease the threshold, the ratio between successful and missed the false alert increase up to 90%. Okay, and so if you want a larger threshold, so this ratio will decrease. So in the present time early warning system, because of the uncertainty that we have discussed in the previous question, we have necessarily false and missed alerts accompanying the system. So we have to be tolerant. So what we are doing is to try to minimize missed alerts, which are the most dramatic. If I miss an earthquake and I have damage, that I cannot do nothing. But if I given a false alert, okay, I have a false alert, but no damage occur. So what we are doing generally is to set the system in such a way that false missed alert are minimized. And in this case, false alert may be higher. So the idea is that generally users should be false alert tolerant for this system today.
Okay. Yes, false alert. And you said that there is no experience, but I have a question here on the railroad by Hakim Ayadi. Hakim Ayadi is the director of research on seismology at the research center. And he says the capacity of faults to reach the surface and generate surface ruptures, how are these sources considered in the earthquake early warning system, especially for railroads?
Building a railroads crossing a fault is really a good point. But the example of Turkey, where we have a relatively shallow earthquake of magnitude 7.8 and probably a lot of surface breakage, is relevant. Provided that our network is well distributed around the epicenter of the future earthquake, I don't see major problem into well identify the effect of the event in the rapid interval after the event occurrence. Okay. In the case of, as you have seen from my application to the wave company, since they are using their own system, and there is a reason for that, because the system must be certified in terms of quality, speediness, robustness, security, all these issues. So they are using their own system. There are some limitations because actually the geometry of the array does not allow to do earthquake location, for instance. Okay, but in that case, we can. We hope that we are, after the simulation that we have done, we hope that we can identify the segment that was affected by big damages as the one that are mentioned in the questions. This fault crossing the railway must generate high amplitude shaking waves. That is the scaling law earthquakes. If the earthquake is large enough to produce faulting at the surface, the energy associated to the waves that are radiated by this earthquake are sufficiently high to be recorded at increased distance. And so this is the data that we use.
Okay. You recorded in terms of PGV, yeah?
Yes. PGV, PGA.
PGA, yes. PGV, yes. Hakim, he adds that, and this is true, that during the Alasnam earthquake in 1980, the railways, they were completely bended and torn away, and that's why, I mean, the crossing, as you said, the crossing of faulting with the railway is a specific case for the and this can send a specific signal to the stations for the early warning system. So this is what he says, and
it may happen that the specific sensor located in this damaged zone will not work during early warning. But indeed, if you have a line of sensors, the other will work. Okay, and the information is given. However, this is the main idea behind this kind of systems.
Yeah, yeah. I know that there are some fast train projects in Algeria. I know that the project from Jelfa to Boumedfa, which is in the center north of Algeria, crossing the Tel Atlas and everything. And but I don't know if there has been any warning system associated with the railway. I don't know if anybody knows about this, but I don't know. This is there are other projects, and I don't know either if they have any warning system linked with the seismic network. And no, I think it's you have been successful. Many participants, and it reached 27 participants here in the Zoom, but I think in the Facebook there has been I think also many other participants. I don't know the number, but just maybe another question, and the last question, because it has been now 1.5 hours that you are on the stage, Aldo. I think it's the time to go and have some lunch, right? Last question is, what is the biggest limitation in earthquake early warning systems? The window of time, the false alarms, the magnitude estimation, the seismic intensity estimation. So I think this is kind of a summary of the questions that have been sent to you, and this is asked by Said Maush, who is also at the research center in geophysics. Said is working in seismotectonics in NATO.
So
a summary. A summary.
These points are indeed the weak point on which the community of scientists working on early warning systems is working today. In particular, we don't use a fixed time window because we observed that using a fixed time window, we can have underestimation of the prediction. False alarm, I have already discussed the fact that in some sort for present time early warning system, we must be tolerant to false alarm, but the application that we show, essentially the one in Turkey, shows that we can stay at the level of 90 successful to 10 false alarm percent. The magnitude estimation in this impact based method, the magnitude is less important than in the source based method. And seismic intensity estimation, okay, I use seismic intensity because engineers, shake map, they give the information in seismic intensity, but the basic parameter that we estimated is the peak ground acceleration or peak ground velocity, okay? So the matter here is how to convert this value in intensity, but nobody excludes that you can make an alert on peak ground motion itself. In this case, you don't have any problem with the conversion. Okay? I don't know if I succeed into answer all these questions.
Yeah. Okay. Thank you very much. Something I didn't mention at the beginning is that you received a medal from your president of Italy and once. So this is a great honor that you received. Okay.
Long time ago.
I hope when you come to Algeria, and I said this is a message sent to our friend, the director of the Research Center of Geophysics, Beljoudi. He just intervened previously. I think Algeria will provide you also with the honor when you will come. I think so. No, you came here already. You were
Yes.
here in Algeria. You came in Algeria already in 1990 or 1989. I think it was good.
It was
Yes.
just after
Yes.
my thesis.
Yes.
So it was 1990 or 1991.
Yeah.
Yeah.
Yeah. I know that you enjoyed
Yes.
your stay.
Yeah.
Yes.
A lot.
Yes. Yes. Murad. Yes. You remember this.
Yeah. I remember. Thank you,
Okay.
Aldo. Thank you very much.
Yeah.
Thank you for this invitation. It was really very.
Maybe you will receive a certificate of participation for this webinar from our colleague and the mentor of this site, Fouzi Belalem. So it's up to him. Yes. Yes. Yes, Fouzi, you can say something.
C'est Beljoudi.
Beljoudi?
Vous m'écoutez?
Oui, on t'écoute, oui.
No, just last word before finishing this presentation. I'm open for any cooperation with Italian university and European university to share your experience, because the CRAG also has his own experience. We have our own experience in seismic alert monitoring. We have started in 1980 after the earthquake of El Aslam with 7.2, and we have I think manage and monitor a lot of seismic events. Now we have a classical or a basic network, seismic network. We have an alert in 2 minutes after the main shock. After a shock, we receive SMS, emails, and Android program application, and we receive in 2 minutes after the main shock or after the earthquake, we receive the first alert. But we need to make our network more performant, okay? And this is need the work of a lot of people, the people who have working on the earthquake early warning system, and now we project we will buy about. I have asked for 300 seismic station from 2025 until 2035, and we will densify first because the first step is we need to densify because we have some region where we have a lack of station, and we need to densify first and to go at the south of Atlas Sahara because we record some earthquake here, and we can also we can have earthquake like to recorded or occurred in Morocco, and at the end I want to thank all people who has contribute to this presentation, especially Mr. Professor Aldo Zollo. Thank you, Mustafa. Merci. Merci.
Okay.
Merci pour tout.
Okay. Thank you. Thank you, Hamoud. There's also one maybe last things that Yahya Mohammadi wanted to say something. So please, Yahya, you have the. Yahya
Yes,
is organizers. Okay.
Yes. Okay, Mr. Maghrawi, thank you very much. I would like, we would like to express our heartfelt gratitude to several individuals who made this conference possible. Firstly, we extend our sincere thanks to Prof Aldo Zollo for delivering this valuable conference, and of course, to Prof Mustafa Maghrawi for moderating the webinar and supporting us at GeoHazard community. We are also very grateful to Prof Bzagoud Morad for his assistance and for providing the Zoom link. Our thanks go to the CRAG, particularly the director, Mr. Beljoudi Hamoud, for allowing us to host the event and support this conference. Special thanks also goes to Mr. Dr. Shafiq Aidi for his technical support. The event was made possible by the combined efforts of GeoHazard community group and the GeoLearn Hub platform on Facebook. Many people contributed to the success of this meeting, including Dr. Fouzi Bilalam and Dr. Saeed Maouche. We are especially also thankful to Mr. Tizrawi Abdelrazak for his technical support in the website. Lastly, we thank our GeoHazard community for their encouragement and support. And see you next time, inshallah.
Thank you. Thank you, Yahya. Thank you, Aldo. Aldo, so the people are waiting for you in Algiers now. Okay. You are constrained, but it's only 1 hour from from Naples. You see, it's very close. Yes. Okay.
Very happy.
Murad, do you want to say something? The end?
Thank you all. Thank you, Fouzi. Thank you, Mustafa. Thank you all the colleagues, and very many thanks.
Yeah, we don't hear you, Murad. The microphone.
Yes. Thank you. Thank you all. Sorry. Thank you all, and thank you, Aldo. And I hope to see you in Évora.
Yes.
In the end of this month, Mustafa will come here in Évora. And the next, Aldo, I invite you to
Algiers.
visit.
Thank you.
Algiers too. Yeah.
Okay.
Thank you.
Okay. Merci.
Merci
Merci
à tous.
Mustafa, merci à vous tous.
Ouais, merci.
صح.
Muslima.
Fouzi, restez en ligne. Mustapha et Yahya, restez avant de couper.
Okay. I tell
Okay.
you goodbye and thanks again.
Thank
Bye-bye.
you.
Thank you,
Goodbye.
Aldo. Bye-bye, Aldo.
Ciao.
Bye-bye.
Ciao, ciao, ciao.